Welcome everyone to a podcast. Today I'm going to be talking about the COVID vaccinations and the anti-vax movement in general. So before we get started, a few things I want to point out. First of all, I'm not an expert in this. I believe I have enough biology knowledge as a biology student to debunk these claims, but if you do want some actual specific advice or specific knowledge, then be sure to ask your doctor or any other expert or search online. There's so many resources that make you more comfortable with vaccinations and vaccines. Secondly, I have cut this podcast into several pieces just so I don't have to record it all in one go. So if there is a awkward transition, then I do apologize. I will try to make everything nice and smooth, but like I said, I do apologize. Thirdly, I have used some sources here and I'll put them in the description. If you think that I've missed a source or you even want to add a source of your own, then be sure to comment and then I'll add it. And fourthly, if you do have any questions, be sure to comment them. I may actually make a podcast or a video that answers these questions. So yeah, without further ado, let's get started. So obviously last year in 2020, COVID had a huge impact in our daily lives with lockdowns, etc. And people obviously getting infected and dying, and also, which people don't really realize, having quite sometimes even permanent effects on their health. Now, what really is the end goal? How do we really want to defeat COVID? Well, let's think about this. Bacteria, we have many ways of defeating bacteria. So, for example, the Black Death, which has ravaged Europe and I believe parts of Asia in history, is caused by a bacteria, and so we have quite a variety actually of methods of dealing with bacterial infections. So, we have principally now we have the antibiotics. So these are chemicals that somehow disrupt bacterial function, how they reproduce and build, etc. But now we have, or at least developing, more sophisticated methods such as viruses that target bacteria and other quite cool stuff actually. But we don't actually have anything like that for viruses. They are, well, quite small. They're not that specific. They aren't really living things, so you can't really, stop them functioning by, stop them reproducing or so on, because their way of reproduction isn't like that of bacteria or even animal cells or plant cells. So really the only way we have right now of stopping viral infections is just letting the body do its thing. And obviously sometimes that works, and in many cases as well it doesn't. So that's what we have. We have vaccines that basically train our body to recognize and disrupt and kill the viruses or the viral infections in particular. And there are a huge variety of ways they do that, and it's quite sophisticated and quite cool. But I won't really go into the biology because not only am I not really that confident in it, but it's unnecessary. So a little bit of history of vaccinations, which I believe I talked about a little bit in my last podcast. But the first vaccine was for smallpox, which at that time was, again, a ridiculous disease. It was very powerful. It had quite a high lethality rate and it was quite infectious. And essentially, in so many places in the world, it run riots and it killed many people. So what happened was, quite simply, a very smart biologist found that people who were infected with cowpox, which was by far a less serious disease, but people infected with that didn't succumb or didn't even get infected with smallpox. So he took, I believe it was a cow maid, which I don't think in our modern health and safety and our ethical beliefs, I don't think we can do that. But he took a cow lady or cow maid and infected her with cowpox. So directly gave her, I think it was like a pus from a sore. And after she got cowpox and then recovered, he then did the same with smallpox. Now, normally, if someone was given, smallpox into their bloodstream, whatever, they'd get it quite quickly and quite likely die. But as for the cow maid, she didn't at all. And that was how basically the first vaccine was invented. And we've obviously, through the hundreds of years since, developed far more sophisticated vaccination programs and vaccines that don't require us literally spooning out pus from an infected person and putting it into ourselves. But at the same time, this is kind of the same principle. So the body recognizes something which are called, antigens. So recognize a particular form, well, not a form, but something that is specific to, well, in this case, a virus, and it then causes it to trigger an immune system reaction that allows it to fight back against the infection. And we know this is quite useful and quite efficient because we've literally now since eradicated smallpox. So apart from a few small labs in Russia and the US, I believe, smallpox doesn't exist in the wild population, so i.e. us. This is obviously huge success for vaccinations. It shows they work. And smallpox isn't the only disease that we've eradicated. There are other things as well, I believe, like polio. Polio, again, used to ravage through many communities, many countries, and it especially was a very nasty disease that you 100% don't want to get. But luckily I believe, eradicated it. I don't know if we eradicated it or like put it down to such low numbers that it's barely detectable. But again, that's a huge success for vaccines. So the question remains is why then is there such blowback? Why is there so much resistance to vaccinations? So now I will go through a few reasons why I believe so. So in my opinion, there are two legitimate reasons I feel like for fear, or at least discomfort with taking vaccines. The first one is how long it takes to develop vaccines. In particular, the COVID vaccine took very little time really to actually develop. Now I'm going to talk through, as you can see here, there's a web page I found on the normal development of vaccinations. So normally it'll take, as we see, where is it? So normally it'll take around, here we go, 10 to 15 years to develop a vaccine. This is all the way from the initial conception to through all the testing and so on and the rollout, and then that takes around 10 to 15 years. Obviously the COVID vaccine took less than a year. Now let me just go through some of the stages to further understand this. So first of all, we have the exploratory stage, which is where you kind of find detail out what you want to do. So you might, as it says here, find out the antigens that you might want to use in order for the immune system to recognize a disease. And so you might want to either isolate this from a bacteria or a virus, or you might make it yourself. And again, as you can see here, it could include virus-like particles or weakened viruses or bacteria. So when they say weakened, they don't really mean things that can actually go and kill you, but they've taken out, so for example, the bacteria's ability to make toxins, or they even some other way alter the virus or bacteria so it's not as powerful and won't actually kill you. Or it could, for example, as it says here, bacterial toxins or other substances derived from the pathogens. So these are things that they've identified that can be used as things that the body or the immune system can recognize in order to then trigger the immune system response. And then we have various stages where they go through and they test in increasing increments of people or first animals the response to the vaccine. So for example, maybe in the first stage they might see, well, this works with this and this efficiency, and these are the side effects here that we've documented. And then they'll go back to maybe the drawing board or to a planning stage, and they'll say, well, okay, fine, we need to maybe change this or add this ingredient and so on and so forth to make sure that both the efficiency and the side effects are acceptable. And essentially then they move on to various different vaccine trials. And again, normally the usual difference between the trials is that there's more people and there's also more involved experimental procedure, so perhaps some placebos and different things, and also various people of various different biological makeups, so different races, for example, or different people, different allergies, different ages, different environments, and so on and so forth. Just basically to cast out your net as wide as you can to see if there's any potential issues, like I said, with either side effects or with efficiency. And then after that, you then roll it out and make sure that you have some kind of way of monitoring basically if anything happens, and so you can either take it back, as some vaccines have been taken back, or you can add extra things to it. So maybe you can modify it a little bit, or you can change the way it's delivered. So maybe, instead of 2 shots, 1 every week, you can say, okay, well, for example, let me give 1 shot the first week and then wait a month and then give the second shot, and so on and so forth. So yeah, this is typical, let's say, rundown or typical time frame of making a virus from scratch. And like I said, this source here will be in the description. So here I have the Pfizer, so I chose the Pfizer vaccine. So the Pfizer official handout for their time frame and other things, obviously, for the implementation and the development of the vaccine. I think it's the development, not the implementation. Obviously, this will be in the description as well. So as you can see, they first got the genetic sequence in January the 12th, 2020, but then they actually submitted it in December the 1st, 2020, or even in the US, November the 18th, 2020. So that is, 10, 11, 12 months, which is obviously quite a bit shorter than 10 to 15 years. Now, how is this the case? Remember, there are quite a few reasonable explanations for why this was developed so quickly. First of all, as you can see here, they went through all the trials. So they have phase 1, 2, and 3. And in phase 3, after obviously quite a bit of investigation, they found that the efficiency or the efficacy rate of the vaccine was quite, that's quite good, 95%. But also, the side effects were well documented and they were deemed acceptable for general, mass rollout. Now, secondly, you need to realize that there already has been quite a bit of, like a fair amount of research into coronaviruses. So COVID-19 or SARS-CoV-2 is, as you can see by the name, not the first coronavirus. We actually had SARS-CoV-1 and we also have MERS as well. So we had 2 previous coronavirus outbreaks which didn't cause as much issues as this one, yes, but it still caused enough issues to be of concern. And so there was, as normal, vaccination development, vaccination research. But because those infections, those viral outbreaks died down, the vaccination research was ultimately cut or at least benched because there wasn't really any need. Not many people were dying and getting infected. But obviously what this means is that right now, when we have a new coronavirus, the development for a vaccine is already, we already have a head start, and that we already have started development on vaccines for 2 previously, similar coronaviruses. Now, secondly, for vaccination and vaccine development, normally you don't get that much funding and that much pressure. However, for this one, we literally have a worldwide pandemic, and many governments are willing to invest a lot of money, obviously, to try and curb the spread and the infection, and then soon hopefully get life back to normal. And normally for a lot of scientific research, the main problem is funding. So you have your amazing idea that you've put down, and then you know exactly how you're going to develop something, and you know what model you're going to use and how you're going to get all this, that. But then you realize that it's far, far too expensive, and obviously you'd love to have the money, and then you can make amazing scientific breakthroughs, but ultimately you aren't going to get the money. But here, money wasn't really an issue, which is, every scientist's dream, except here, because it's literally a pandemic that's causing this amazing amount of money. So we have here a major block to the pace of scientific development, i.e. money, removed because obviously people want to stop the pandemic. Now, thirdly, the reason why this vaccine was developed so quickly was because it's an mRNA vaccine. Now, I'm going to talk about this later. The mRNA vaccines basically allow the body to encode part of the protein found in the virus. The body obviously realizes, hey, wait, this protein is found, on a virus. It's not actually found in the body. We don't actually make this. And so that will trigger an immune response. And then when the virus actually comes rolling around the nose and into the lungs and wherever else it goes, with that protein encoded by the mRNA, the body already realizes that this is a foreign thing and already has a plan for the response it's going to have, so we can fast roll out that plan and deal with the virus very quickly before it can take proper hold. So these are a few reasons why this vaccine took, far less to actually develop, or far less time to develop. So the second reasonable, I'd say, objection to vaccines is the risk of side effects. Now, I say it's, reasonable. At the same time, the risks are small, the probabilities are quite low, and significant amounts of development of vaccines, or amount of time of development of vaccines, goes into eradicating or at least managing the side effects to an acceptable level. Now, if you think about it, this makes sense because you want your vaccine, obviously, to be quite powerful, to be efficient at dealing with what you want it to do, but at the same time, you don't want it to kill the person. That's kind of counterproductive, not really what you want to achieve. Now let's talk about deaths from vaccines. So I have a number here from the smallpox vaccine, which obviously we don't need anymore. But apparently, and again the source I will put in the description, 1 to 2 people per million die from the smallpox vaccine. Now, there's an added benefit, or an added, I won't say benefits here, added good points here in that those people are also, likely to have a compromised immune system. So if you have a compromised immune system, your risk from dying, already from the vaccine was 1 to 2 per million, which is quite low. And obviously it would be far lower if you don't have a compromised immune system which can't actually deal with it. Now let's put that into comparison with some other odds. So the odds of being struck by lightning, that's assuming you live for 80 years, is 1 in 12,000. Now, 1 in 12,000, obviously, it's fairly rare, but it's far more likely than actually dying from this particular vaccine. Similarly, something that we as humans find quite deadly, which is not quite true, is sharks. Now, sharks are funny in that they don't really go for us anyway, but maybe another podcast I'll talk about our misconceptions of animals. But dying from sharks, actually, the probability of that happening is 1 in 8 million. So as you can see here, our conceptions of dying from things are quite out of proportion. Dying from a shark, which we consider, very scary animals, is 1 in 8 million. And similarly, vaccines, which we think are quite scary, is 1 in 2 million. Now, what that could be is just, our brain used to dealing with things that are bad, inflating probabilities, saying that it's quite likely to happen, which, back in the cave days, that's quite useful. If someone told you you're, this amount likely to die from a tiger, then you'd say, oh, it's a tiger, that's quite scary, I don't want to die from a tiger. But then if they, actually made it numerical and said, well, actually you're more likely to die from a log falling on your head, then, it kind of takes away that danger, which isn't very useful because you don't want to die from tigers. So that could be why we think that vaccines, or the risk of vaccines and their side effects, are quite high, because, our brains are wired to inflate probabilities of negative things happening just because it's quite useful if you think about it. Okay, so now I'm going to be talking about some objections to vaccinations that I don't find reasonable at all whatsoever. We start off obviously with the classic, vaccines cause autism. Now, do vaccines cause autism? The short answer is no, the long answer is no again. Vaccines just don't cause autism. Now, this has been an issue that has plagued the medical community ever since that one guy wrote that one paper, and then he was found to have been funded and bribed, and then his medical license was cut with scissors and thrown in the bin, and that paper was retracted. And since, many, I believe thousands of papers have actually said, no, vaccines don't cause autism, here's, how we know. Now, do we know what causes autism? Not really, or as in we don't know the development of it, and how it progresses, and so on and so forth. But we do know that it has a very powerful, very strong genetic risk-associated factor. So, obviously, you can't really change your genes, as we'll talk about later with vaccines. Now, why do we think vaccines cause autism? Now, again, there was that one paper, but also, I believe the vaccines implemented at that time were given at the same time as the first signs of autism actually begin to develop. So, obviously, a very caring mother would see her baby being jabbed by some chemicals that she doesn't know the workings of, and then, a few weeks later, she realizes that her baby's acting kind of weird, not doing the same things that all the other kids that her friends are doing. And so, obviously, the baby or the child at that point gets diagnosed with autism, and the mother is quick to do the classical correlation equals causation fallacy and think that it's the vaccines that cause autism. Now, this isn't the case. How do you know it's not the case? Well, first of all, like I said, we know kind of what causes autism, and also, if you do the statistics, the vast amounts of vaccines that have actually been given, and then you look at the cases of autism from people that have had the vaccines, and you see that like a very small number of people who've actually been given the vaccines were then, then developed autism. Then you can do some fancy statistics and find out the probability of them actually being given autism from the vaccines is very low, so it's basically impossible. And not only that, there are then other studies that show that, okay, this particular thing in the vaccine doesn't do this to make you develop autism, and so on and so forth. Now, it is a really frustrating thing because from a medical standpoint, it is so obvious that vaccines aren't caused, autism isn't caused by vaccines, but some woman in Facebook thinks that. And, there's quite frustrating things I've seen on Facebook, things like, quite blatantly throwing away science for their own feelings, talking about, no, it's not genetics, it's vaccines, and it's like, just because you don't want to accept that, it's your genes that caused it, yours and your partner's genes that caused this, which, is quite nasty to think about, but at the same time, it is what it is, but there isn't that, acceptance that that's just how it is and moving on. There's always that kind of blaming on things they don't understand. So you've heard it here for like the millionth time, vaccines don't cause autism, and it's a huge problem, that misconception that we have to deal with. Now, I will also link a book in the description that, someone recommended on some page I found, which talks about this issue, this uphill battle that the medical community has been facing regarding the vaccine caused autism, blatant lie. Now, another common objection that anti-vaxxers have to vaccinations is the ingredients that they have in them. Now, this basically just comes from a really huge misunderstanding, lack of understanding of chemistry. So let's just do a quick, what did they call them? Thinking game, and talk about some chemicals. So, for example, we have things like hexyl acetate, hexanol, camphor, octanol, methylpropanol, butanol, and so on and so forth. Now, if you go to a random person in the street and say, hey, do you think these are dangerous chemicals? Would you like them in your body? Obviously, they'll be like, oh no, those sound like very dangerous chemicals. I don't want them anywhere near me. However, these things are quite common, not only in, apples, like in this example, but other food stuff as well. And basically what it is commonly found substances just with their chemical names, which is quite useful in chemistry because in their name it can actually describe the structure and so on of these chemicals. But obviously to your average Joe or Karen, they wouldn't actually know what these things are because they're not actually well versed in chemistry. There's another famous example, which is the classic dihydrogen monoxide. Now, if you told the average person, hey, dihydrogen monoxide is a very, very, very dangerous chemical, everyone who has had it has actually died. This is, a fact, well documented, and in the body it can cause huge problems, and it needs to be pumped out and so on and so forth. But at the same time, it's in a lot of our commercially available foods, such as, like I said, the apple, and things that you think are quite healthy. At the same time, as I've just said, it's quite dangerous and it can cause death quite easily. But, it's obviously the government trying to hide it and, in plain sight and so on and so forth. But there's actually been a real conspiracy or real thought process behind actually, showing off the lack of knowledge here, because the hydrogen monoxide, which people now or back then considered to be quite dangerous and so on and so forth, is literally water. Dihydrogen is 2 hydrogen, and then the monoxide is the 1 oxygen, which is H2O. And so back then, and I think I'll try and find a source for this, if you said the quite, familiar chemical, and the stuff I said about it is obviously correct. I mean, everyone who has drank water has died, and everyone who will drink water will die. That's just how dying and drinking water works. But there's a huge misconception behind the chemical name, that people are then, fearful of it. And again, this could be an evolutionary thing. We are fearful of things that we don't understand, and quite naturally, we don't want them anywhere close to us, and definitely not in our bodies. But again, you need to take a step back and think about things that you may not understand and actually the implications of it. And talking about ingredients, similarly, that stuff that people don't really understand is the concept of dosage. Now, let's talk about quite a common, or I don't know if it's common, but definitely a used chemical in vaccines, and that is aluminium. Now, I believe it's used as, in some way or another to help, push the immune system to react a particular way to the vaccine. But obviously aluminium, you see that in planes and stuff, you don't really want that in your body. And if you think about it, it probably causes all kinds of havoc and so on and so forth. However, in the vaccines that actually have aluminium, the dosage is less than that in breast milk and other milk formulae. And I am a huge advocator for, breast milk and natural milk because, obviously it has loads of good stuff, including, funnily enough, antibodies. But at the same time, this just highlights that the dosage of stuff is important because, again, going back to the water example, if you drink a lot of water, you will die. Now, does that mean that water is poisonous? Well, yes and no, because technically, it can cause harm to your body. But at the same time, it's only if you ingest enough of it that will actually cause issues. And that's the same with every other ingredient in vaccines. I mean, they've gone through, like I said, quite a long development stage to make sure that all the ingredients don't actually cause a huge issue. Now, another fundamental misunderstanding regarding these ingredients is that they're often in compounds. So let's go again to another classical example. Sodium is definitely something you don't want in you. It's highly reactive. It can explode in contact with air. I think it's actually water, like the water vapor in air that makes it explode. And I mean, if you see it explode, it's quite wow. Like a tiny amount can cause a huge explosion. And similarly, let's talk about chlorine, which was literally used in World War II as a poisonous gas. And, soldiers reported extreme discomfort. Should I say World War II or World War One? I meant World War One. So it was used in World War One by the Germans. I don't know if the Allies used it. They weren't really Allies then, but it was used definitely by the Germans as a poisonous gas. And, classical trench warfare, if you see, that, I think it's like a yellowy gas going towards you, and you get very, very, just uncomfortable. I think it affects the eyes and nose and so on and so forth. That's definitely not something you want to put in your body or, anywhere near you. But if you combine those two together, we get the classical sodium chloride in all its deliciousness. Essential for your cooking. If you make food without sodium chloride, I will throw it at you. It's obviously it's a staple part, and obviously it's salt, right? But this shows that we have the two very, very dangerous chemicals. So, sodium and chlorine, if you put them together, then it makes, obviously it's harmful in large doses, but at the same time, relatively harmless sodium chloride. Now, similarly, if you look at the ingredients of a vaccine and you see something which you say, if you look at a particular ingredient, you think, well, that looks quite dangerous. So this is what you need to bear in mind. First of all, is it in, compound with another chemical? So being in a compound in some other relationship with another chemical, another element, changes the properties. So like I explained with the sodium and the chlorine. At the same time, you also need to figure out if the dosage is large enough to actually cause you harm, or large enough to cause you long-term harm. So like I said, with the aluminium, aluminium is, fairly useful in small doses and is in quite fairly high doses in breast milk and other milk formulae that you can get from the supermarket. But at the same time, the vaccines which have the aluminium have it in much smaller dosages. So it doesn't make sense to get annoyed and get scared about the aluminium in vaccines when literally when you were a child you consumed more. So yeah. Now, an objection that people have to this vaccine, in particular, the COVID vaccine, is that it's an mRNA-based vaccine. Now, the reason that people are concerned about this is because, well, there are a variety of reasons, but mainly it hasn't actually been done before. We don't actually have a publicly available, wide rollout vaccine which is mRNA-based. It's normally based on something else. So, like I said, proteins and toxins and so on found in bacteria and, identification stuff in viruses. But mRNA is a new way of doing vaccines. Now, when I say new, I don't mean completely brand new, we haven't thought of it before. The concept of mRNA vaccines and using mRNA has been going on for some time now, and it has been, fairly well researched for dealing with things such as cancer and so on and so forth. And what it does in this particular case is, I don't know if I said it already, but so what mRNA does is in the cell uses mRNA to code its proteins. So, if it has a particular mRNA sequence, it will then read it and say, okay, well, I need this amino acid here, and so on and so forth. And then from that, it will build its protein, and then, it can go on and do whatever purpose that protein does. So, obviously, proteins aren't exclusive to us. COVID virus, as well as other viruses, obviously have them. And in particular, they have the COVID virus. It has a particular spike protein, which is quite distinct to itself. And so what this vaccine does, the COVID vaccine, is it takes the mRNA, which encodes the spike protein found in the coronavirus, and then tells the cell, okay, make this spike protein. Now the body realizes that this isn't, once the protein's been made, that this isn't a protein that you normally find in the body, so it clamps down and it cuts it off and it deals with the cell appropriately, which often means killing it. But at the same time, the body would then realize, okay, whenever I then see another spike protein, which has been encoded by the mRNA that was injected into me, whenever I see that spike protein, I will know then what I need to do. I need to do this and this and this, and so on and so forth. So that means that when the actual virus comes along, then it can deal with it appropriately. Now, the common misconception about mRNA is that people see, mRNA, DNA, they're quite same. They're basically the same, aren't they? And so people think, okay, well, that means if I'm injected with this vaccine, it will then recode my DNA. Now, this is a blatant misunderstanding of biology, and in particular human biology. We don't have the machinery to turn mRNA to DNA. Now, funny enough, it's actually viruses which can do that, but not the coronavirus. But RNA comes from DNA. We obviously have different types of RNA, not just mRNA, and it doesn't go RNA to DNA. Now, something else that's quite silly is that people don't realize how many cells we have in our body. You most probably can't with a single injection or two. I think for Pfizer vaccine is taken twice, so you get 2 jabs. But either way, you can't recode the trillions of cells, or at least hundreds of billions of cells in your body, which most of them have DNA. You can't then, with one single jab, recode every single one. That's silly. And like I said, we don't even have the machinery to do that. It is literally one way from DNA to RNA, at least with the machine that we have in our bodies. Now, carrying on from silly theories about the vaccine is the microchip theory. So people, when I say people, often people who don't know biology, I'm talking on Facebook, not any actual recognized and respected scientific authority, but they talk about vaccines having microchips in them that do something or other. Now, the more you think about it, the sillier it is. First of all, microchips are obviously, as per the name, micro. However, funnily enough, the biology of a human body is also micro. In fact, it's micro on a smaller scale. Now, we first have the issue of miniaturization. Miniaturization, so making things small. Now, it's already hard enough to cram loads of machinery and electronics into, something small like a computer chip or so on and so forth. But then trying to cram something into, a package that is small enough to fit in the body, that's another level of engineering that I believe is beyond what we're capable of at this point in time. And it is quite important that you make it small enough, because obviously if you're injecting a vaccine into the blood system or the bloodstream, then if it's too large, it will cause a clot. It will stop blood flowing. I mean, you don't really need to have that big of a clot already to, cause severe issues. So imagine then introducing a chip, like a piece of, equipment into the system. Now, there's obviously other issues as well, such as the body will probably not like a foreign thing inside the body. So we already have, our body immune system is already so sensitive. So that's why we get, for example, things like allergies and so on and so forth. It attacks things that you really think, why is it attacking this? Why are peanuts? Peanuts aren't deadly unless the body decides it's deadly. I mean, that's how silly the body is with the foreign objects. So you really think it's going to accept a microchip? Now, obviously, you can, make your vaccine so you make a vaccine, design your microchip so that it, seems all natural, doesn't display any characteristics that the body sees as foreign. But then that's again adding another layer of complexity onto the microchip, which is already going to be quite complex in itself. Obviously, there's the issue of what do you actually want the microchip to do. So I already talked about how complex the body is. So the question is, what is the microchip doing? Is it actually changing how your body functions? Well, if it does that, then it has to change so many things at once and all coordinate at the same time and so on and so forth. And then we go to the problem of, well, how's it going to do that? That displays a level of biology that we simply don't have. We don't understand that much biology. And then, even if we understand that, we then are going to cram that, like I said, into a small package that won't actually interfere with the bloodstream. That's silly. And you need to think about, things such as tracking and so on and so forth. Like, why does the government need to put microchips in us? The government probably knows far more than they're willing to tell about us. Like, I'm pretty sure, okay, I'm recording this podcast, but I'm pretty sure, okay, I'm not in America, so someone in MI5 is also recording me recording the podcast, especially with some of the things I've said in group chats and so on. So, the fact that they then think, okay, we don't have already enough information about this individual, we're then going to engineer it. Engineering a microchip, like I said, is like such a feat of engineering that it would take so much development time, but then we're going to engineer that to get what out of it. Obviously, I'm not part of the government, I'm not part of this conspiracy, I don't know, so there could be, something that they want to know in particular, but it just seems unfeasible to go down this very, very long route of, like engineering loops that they have to go through to make such a thing that then doesn't really achieve much. It doesn't really make sense. So to conclude, the anti-vax movement is full of it, really. There are many, many things wrong with what they say, and this is in particular obvious in the fact that it takes me, and I'm second year university biology student, but I don't even study microbiology and immunology and so on. I study things like animals and ecosystem statistics, but even with my basic knowledge, I can still debunk their claims without even, doing too much research. So that really talks a lot about the validity of their arguments and how it's really just rooted in misunderstanding and lack of understanding and arrogance. Now, talking about arrogance, I believe I talked about the Dunning-Kruger effect in my last podcast, but I'll revisit it here because it's especially important. So imagine if you are looking at a graph, right? But the graph looks like a valley. So if you're standing in a valley and you look along the valley, there's like a dip, and on both sides is like a hill. So in the graph, if you believe the bottom or the x-axis is how much you actually know of the subject, and then the y-axis, or going up and down, is how much you think you know, how much you're confident in that subject. So Dunning-Kruger effect basically says, okay, at the top of the valley, in the left, you don't know much, but you think you are the best at it. You are amazing. This is where the anti-vaxxers are. Now, as you learn more, in this case, biology, you start going down and down and down the valley until you realize, okay, there's actually a lot to learn, and so I basically don't really know much and I have so much more to learn. And then you continue traveling along, and then you reach the right side of the valley, and you start going up when you think, okay, I've learned a lot, I believe I'm now confident and qualified in what I am saying. So basically what I am saying is the answer to the anti-vax problem, which is a huge problem definitely, is education, and that is in many forms. So perhaps biology, not everyone, I don't want to come out and say not everyone has a talent for biology, but not everyone has the patience for biology. And so we can talk about, this how vaccinations work, and this ingredient does this to the body, and then the cells react to this and that, and people talk about white blood cells, but there are like huge variety of them, and then this one does this. So this is, obviously once you understand this, you realize how silly the anti-vax movement is. But at the same time, the anti-vax movement is full of people who don't really have time for this. People, mothers who are worried about their children, who don't really have time to open up a biology textbook and go and, read loads about biology. So other forms of education could simply be just showing them how effective vaccines have been. Now, I've read about an effective way of persuading anti-vaxxers to, come to the bright side is by having them look at the effects polio has had to children. And children in particular, because, you get an emotional connection. And this is why I say polio is a nasty disease, because it can literally ravage through your body. And you obviously, look at the iron wars and so on of what polio has caused, and you see, okay, well, we don't see that now because of literally vaccines, nothing else. We have an effective vaccine system and program and rolled it out, and we've eradicated polio. And so I believe this is, so the two ways I think of preventing the anti-vax movement of spreading is, first of all, spreading, for example, this is my podcast which I just recorded, so answering their objections to vaccines, but also telling them, look, we have had a very, very good track record with vaccines. We are, at this point, hundreds of years into developing them. We are pretty good at them. We know how to do them. Obviously, it takes time and effort to make them, but we've already learnt from this, and you can see that we've learnt and we're successful in it because we don't have iron walls for polio anymore. People aren't dying from smallpox, and things like measles and so on are in sharp decline, even though they're going back up again because of this anti-vax movement. So this is really all I have to say. So please do share this podcast. Obviously, I want to grow my channel, but just so people understand that, or anti-vaxxers understand in particular, that their objections aren't new. We already have answers to them, and the answers are quite sensible. And so yeah, thank you for listening or watching. Hope you've enjoyed. And like I said, please do leave any questions you have in the comments, and I'll try and answer them either in the comments or in a separate video. So yeah, make sure you like and share, and goodbye.